Hi, I'm Alec, and today I want to talk about a fundamental algorithm in machine learning called a decision tree classifier. By the end of this video, you should walk away understanding what a classifier is, what a decision tree is, and how to train a basic decision tree classifier. This video is for anyone with an introductory understanding of computer science and basic probability. Before I dive into the specifics of decision tree classifiers, I want to introduce a useful toy dataset that I'll be playing around with for the rest of the video. It's called the iris dataset, and it consists of 150 examples of iris flowers. These flowers have three different types or classes: iris versicolor, iris setosa, and iris virginica. For each flower, we have four measurements: the petal height, the petal width, the sepal height, and the sepal width. We want to classify or separate each flower example into its respective type by only using the information from these four features. Here is a basic scatterplot of the iris features. For simplicity, I'm only considering the first two features in the dataset, the sepal width and the sepal height. Each point corresponds to a flower, and each color corresponds to a specific class of that flower. A decision tree in its most basic form is a single conditional where we say, if a certain feature is less than a specified value, then it belongs to one class, otherwise it belongs to another class. Shown on the screen are two shaded regions. We are predicting that each point in the blue shaded region is a setosa flower, and that each example in the green shaded region is a virginica flower. Now, this might seem like a very crude way of classifying data that probably isn't very accurate, but this simple system of breaking up data into different sections based on conditionals is the essence of a decision tree. This is in fact a decision tree classifier in its most basic form. The tree diagram on the right is a visual depiction of a decision tree. It says if an example has a sepal length less than or equal to 5.2 centimeters, then it is predicted to be a setosa flower. If the sepal length is greater than 5.2 centimeters, then the flower is predicted to be a virginica flower. These two diagrams are just two different ways of expressing the same idea. You can achieve pretty good performance from a simple decision tree classifier like this one with only one conditional. This tree actually predicts the correct class of the flower 59% of the time. That's much better than a random 33% of the time. We can make this classifier better by further splitting the data with another conditional. We can say that all the examples with the sepal length greater than 5.2, if they have a sepal width less than or equal to 2.6 centimeters, then they're a versicolor flower. Otherwise, they're a virginica flower. This forms a slightly more complex decision tree classifier with a better accuracy of 63%. This process can be repeated indefinitely to form complex decision trees. Now that you hopefully understand a little bit of the intuition behind how decision trees are structured, you might be wondering how these trees are learned. Before we delve into the learning algorithms behind decision trees, we need to understand the concept of information entropy. This is distinct from the entropy you'll learn about in thermodynamics. Information entropy can be thought of as the level of uncertainty in a probability distribution. Another way of thinking about it is how spread out a probability distribution is across its possible states. In this example, we have a basket of balls of two different colors. We have 5 blue balls and 1 orange ball. We can represent the probability of choosing a ball of a certain color with this histogram on the right. In this example, the probability is very concentrated on a single one of the possible states, namely blue. This represents a probability distribution with low entropy, because the probability is not spread out across the possible states, it's concentrated on a single state. Here's another example where we have 3 orange balls and 3 blue balls. This is a uniform distribution of ball color, where the probability is spread out as much as possible across the different states. So this corresponds to a high entropy probability distribution. Now that you've seen some examples about entropy as a concept, it's useful to understand some of the math behind it. This equation represents entropy. H of x is equal to the negative sum of the probability of x times the log probability of x. X just corresponds to a random variable. So in the example case with balls, it was the ball color, but that could be any random variable for a specific probability distribution. And I know this equation might seem a bit unintuitive at first and inaccessible, but I find that looking at it in a couple of different ways helps to connect it back to the examples that I showed you guys previously. The first thing you might notice is that the equation looks a lot like an expected value or a probability weighted average. In fact, entropy can be thought of as the expected value of the negative log probability of x. Another thing that might be bothering you is wondering what exactly this negative corresponds to. What is the intuition behind a negative log? Now, if you remember some of the basic log identities from algebra, you remember that the negative of a log of x is equal to the log of 1 over x. So entropy corresponds to the expected value of the log of 1 over x. If we look at these two example probability distributions, this results in a low entropy for distributions where we have a few high probability events and many low probability events. And for a distribution with many relatively low probability events, we have low entropy. Now you might be wondering what this all has to do with decision trees, and that relates back to the idea of information gain. Let's go back to our iris dataset example where we have a set of points, each corresponding to a flower of a certain class. We want to split up the data into two sides based on some value. But how do we choose the optimal value? We want to minimize the entropy of each subset of the data. In this example, our full data set with all of the points is a uniform distribution of class, meaning there are an even number of each class initially. However, if we split the data into the flowers with sepal length less than or equal to 5.3 and greater than 5.3, we no longer have uniform distributions. If you remember from before, a uniform distribution is when the entropy is maximized. So moving away from a uniform distribution can only decrease the entropy. So by splitting the data at this location, we've lowered how concentrated the data is to specific classes. Thinking about it intuitively, a perfect classifier is one in which we have completely separated all of the flowers from each other. Each leaf node will only correspond to one flower type. And this will correspond to a state with low entropy. This is the essence of the concept of information gain. We want to find a split of the data such that we can minimize the entropy of the data on each side of the split. Here we can test the information gain of many different possible splits. Whichever of these splits provides the highest information gain, we can use as a split on our tree. We can repeat this process many times to form more complex trees that better fit the data. Hopefully now you have a better understanding of what decision tree classifiers are and how they learn. Thanks so much for watching this video. Please subscribe, like, and leave a comment if you enjoyed this video.